Welcome to the lesson 21 of the Advent of SysML v2. This is a training series consisting of short videos and exercises brought to you by Sensmetry in collaboration with Vince Molnár. My name is Kestutis, and today we're going to review week 3, everything we've learned in the lessons 15 through 20. This week marked a major shift. We went from static structural models to dynamic analysis, behavior modeling, and professional automation. 3 themes defined this week: analyze, behave, and automate. This is what SysML's v2 textual notation makes it possible. Let's start with model evaluation, transforming static definitions into compiled values. In lesson 15, we learned a critical distinction. Viewing a definition shows you what features exist and their default values. It's a static blueprint. Evaluating a usage computes the actual value in a specific context, considering all the specializations and overrides. Syside Automator provides this computational evaluation through a Python programmatic interface. Here's the key insight. Evaluation scope determines what values you get. The same feature evaluated with different scopes give you different results. Evaluate a feature at a general definition scope, you get the default value. Evaluate at a specialized usage scope, and you get the overridden value. Remember to always ask yourself, whose values do I want? That's your scope. If your values look wrong, check your scope first. That is the most common mistake when getting started. In lesson 16, we took this further with advanced calculations. Built-in collection operations handle counting, summing, and aggregating automatically. Chain calculations resolve dependencies also automatically. Define one attribute based on another, then the third one based on the previous two. Each level depends on the previous, no manual dependency management needed. Conditional logic lets values adapt to system state. One attribute depends on a threshold, another depends on that result. This way, if-else logic can easily be embedded directly into your SysML model. So the key message, your model is now an analytical engine. When you put your calculations in the model, the analysis results will update automatically with model changes. There's no need to repeat the equivalent changes in your Python automation scripts. Now, let's talk about behavior modeling, actions, and state machines. Here's the good news. Behavior models follow the same patterns as structure models. Parts exist in space, while actions and states exist in time. A part definition contains nested parts, while an action definition contains steps, a state definition contains substates. Connections link parts, while successions order actions, and transitions connect states. If you can model structure, you can model behavior. Just think temporally instead of spatially. In lesson 17, we learned the behavior fundamentals, actions. Actions are how we model what systems do. They represent any process or activity, from high-level operations to detailed procedures. Actions accept inputs and produce outputs. They can be broken down into smaller steps. Successions order your actions, specifying what happens first and what follows. Control structures handle real-world complexity, iterate through collections, branch based on conditions, or execute steps in parallel. Assignment actions let you store intermediate results for use later in the process. In lesson 18, we introduced the state machines for reactive behavior modeling. It represents a mode or condition your system can be in, and it captures everything the system needs to remember to decide how to react next. States such as grounded, flying, hovering, idle, processing error. Each state responds differently to the same event. Quick rule of thumb: use actions when you know the sequence upfront. Use state machines when your system waits for events and reacts. States define what systems can be. Transitions define how it moves between them. A transition has 5 parts: source state, trigger, guard, effect, and target state. And when a transition fires, there is a specific execution sequence you need to remember. Firstly, interrupt the source state, do actions. Then run its exit actions. Then run the transitions effect, and then run the target state's entry and its do actions. 5 steps: interrupt, exit, effect, entry, do. Parallel states make all substates active simultaneously. Use these when aspects are orthogonal, like monitoring and control operating independently. But how do you know your state machine actually works? That's where simulation comes in. In lesson 19, we made behavior executable. Think of it like Santa simulating his entire delivery route before Christmas Eve. You don't want to discover a problem with the sleigh mid-flight over the Atlantic. You simulate first. Same idea here. You run your state machine, feed in events and conditions, and watch which states become active. The workflow has 3 steps. Extract the state machine information from your SysML model using Syside Automator. Load it into Sysmic or other open source interpreter for state charts. Run scenarios by triggering events and observing transitions. Our simulation script provided 2 approaches: interactive, step through manually, useful for exploring and debugging, and scenario-based, runs complete test sequence from file, useful for validation. Here's the key insight. Catch the logic errors in simulation, not in production. It's faster, cheaper, and this is what we call validation before implementation. In lesson 20, we closed the automation loop with CI/CD, continuous integration, and continuous deployment. Here's the basic idea. Every time you commit a model change, a CI/CD pipeline automatically validates it. It generates fresh reports and publishes them for stakeholders. This works because SysML v2 is textual. Your model are text files that can be version controlled and processed automatically, and they are executable. Syside Automator can evaluate expressions, traverse structure, and extract any data you need. From there, standard Python libraries turn that data into reports, dashboards, or whatever your stakeholder needs. The CI/CD pipeline we showed performed 3 main steps. Validate step checked model syntax and semantics using Syside Automator. If anything is broken, the pipeline would stop there immediately. Generate step extracted data and created reports, bills of materials, metrics, whatever stakeholders require. And publish step made updated documentation available. Stakeholders need to see the current information. So there's no more "it works on my machine." No more manually updating spreadsheets when the model changes. The reports generate themselves and are always up to date. So the complete workflow is as follows: define models, simulate behavior, automate verification, and generate reports. From manual analysis to fully automated verification pipelines. This is what professional engineering workflows look like with systems as code. So what have we accomplished in week 3? The progression was deliberate. We started with Analyze theme. In lessons 15 and 16, we covered feature evaluation, value rollups, chain calculations, and conditional logic. Then we moved to Behave theme. In lessons 17 and 18, we learned actions, successions, control structures, and state machines. Finally, we tackled automation. In lessons 19 and 20, we explored state machine simulation, CI/CD pipelines, and report generation. That's the week 3 transformation. From static definitions to executable, automated engineering workflows. Your challenge for today is to continue practicing the analyze, behave, and automate workflow with the models you have built yourself. Add computed attributes, create actions, model a state machine, write an automation script that validates the model and generates a simple report. Share your experiences and feel free to ask questions in our community forum. Links and information how to access Syside Cloud is available in the video description. Like the video, subscribe to our YouTube channel, and click on the bell icon to get notified about future lessons. Take care and happy modeling!